Okay, here we are in the materials lesson. We're going to go through these discussion questions. So the first one here, we're looking at a Wii remote control battery cover. And the question is, you see a flexible tab that is pushed or deflected in order to disengage the cover from the controller. Why was plastic used instead of metal for this part? What material property governs the flexibility of this push tab? So Raph, what do you think about that? What material property governs the flexibility of that push tab?
What material property? What do we mean by material property?
Well, we talked about yield stress and modulus of elasticity. What else did we talk about? Let's see here. Ultimate strength, coefficient of friction, density. So which one of those material properties, these 5 that we see right here, governs the stiffness or flexibility of the material?
Well, the yield strength, because we don't want it to get past the yield strength, therefore, because it does, if the force or the stress goes beyond the yield strength point, then the plastic of this cover will deform plastically. Is that plastic deformation?
That's
Which
true.
is the kind of deformation that once the stress is removed, the material does not go back to its original dimensions. So you would not want that. You will want to be on. I'm thinking in my mind that the curve I'm looking at, in my mind I'm a very visual person, and I'm looking at this right here. That you don't want to go beyond that pink point. So whatever the material is, you want to stay in that slope.
So that's true, and I agree with all of that. But yield strength is not the property that governs a material's flexibility.
Well, how close the atoms, the chemical bonds inside the compound are.
Going back to those 5 that we listed higher in this lesson, which one of those? It's one of those. I'll give you that much.
Well, flexibility, Young modulus.
That's right. Yep, the modulus of elasticity. And if you see a modulus of elasticity that has a very steep curve, for example, if we're looking at this right here, in fact, let's see, I wonder if we can, here, we'll just kind of draw on this. Yeah, okay. Well, I've got it here, so let's just draw a little bit. So this, there we go. This slope right here, that is your modulus of elasticity. That's the slope of your modulus right there. So that slope is very steep. What does that tell you about your material?
My material can withstand a lot of stress before it reaches the yield point, the yield strength point.
Not necessarily. It tells you that it's a very stiff material. And yes, usually a very stiff material is going to be associated with a higher yield point. But a steep slope tells you that you have a very stiff material. Whereas a very gradual slope tells you what about your material?
I guess the material has some give, some flexibility.
Exactly. Yeah, that's right.
But it's not more elastic, because based on my research, it says that steel is more elastic than rubber.
I'm not sure how that's defined.
They defined it as because the steel can withstand more stress. That if you go down to, let's see, to this right here, it says that if the steel can withstand more stress, then it is more flexible than the rubber before the steel reaches the plastic deformation stage. So it's not how much you can stretch a material. Elasticity is how much stress a material can endure and still come back to its original form.
Okay, but I mean, if you have a piece of steel that's 1/8 of an inch thick and you have a rubber band that's 1/8 of an inch thick, the rubber band is going to stretch a heck of a lot longer and come back to its original shape than the piece of steel, right?
Yeah.
I'm sure whatever you found, there was some context in which that made sense. I don't really understand that comment right now, but there was probably some context you saw that it made sense.
It makes more logical sense to say that rubber is more flexible.
Rubber is certainly more flexible than steel. No doubt about that.
Sometimes when you learn physics, it just confuses everything.
This is a challenge. I think this is the most challenging lesson that learning objective that we have done. The mechanics. There's a lot of math. There's a lot of concepts that people just aren't familiar with. So it's a challenging learning objective for sure.
Look at me as an example. I'm saying that steel is more flexible than rubber. What am I saying right now? Okay.
I'm sure there was context in that made sense somewhere. But
so we want a modulus number that's low because, right, a lower steep so that it's more flexible.
Yeah, if your modulus is lower, your material is more flexible. But it depends what you're designing, right? If you're designing structural frame for a steel building or something, you want something that's stiff, that's not going to flop around like a rubber band. But if you're designing a rubber band, you do want something really stretchy and flexible.
But for this particular application, the cover here, we want something that has a low modulus number, right?
That's right. Yeah, low enough so that it will flex without breaking and plastically deforming. Yep. Okay. Yeah. So this, that's the whole intent behind this feature right here, is that it flexes inwards. It's displaced in order to disengage it from the rest of the remote control. And then when you release that tab, it just springs back into its original shape because it has not plastically deformed.
For the amount of stress that we're calculating for, when a person puts their finger in there and they put a certain amount of pressure, we're calculating for that pressure. And we're choosing a material that it's going to come back to its original form after a certain amount of stress is put on it. So we have to calculate how much stress we're going to put in it, right?
That's right. Yeah.
Ballpark, at least.
Yeah, and to be honest, for really simple situations, like if you have a straight beam or something like that, it's not hard to calculate those values. But when you get into a little bit more complex geometry, maybe it's not a constant cross-section. Maybe your cross-section changes over the length of the part, or there are, ribs on it or things like that. It can become very complicated, very challenging to perform these calculations. And that's where something called FEA comes into play. FEA stands for Finite Element Analysis. And it's not something that we've really talked about before, but it is it's a computer simulation that allows you to identify the stresses created in a material, when you place a force on it. And so for complex geometry, usually you're not going to perform these calculations by hand. You're probably just going to do FEA on it. For example, SolidWorks, depending on the version that you have, contains a simulation module. A simulation and FEA are sometimes used kind of synonymously, but especially in the student version, I think you get access to the entire SolidWorks suite. Yeah. So there's an FEA tool in there that we're not going to go through now. Maybe we'll talk about that as part of the signature program. But yeah, for complex geometry, you're probably not going to spend much time hand calculating things. You'll just do some FEA on it.
You mentioned something about like an axis. I didn't get the right term, but what is it when you put the pressure? You were using this, and you said there was like
a cross section.
Yes. Are we gonna go over an example here that has to do with the cross section?
Yes. Awesome. Yes, we are. Yep.
Okay. So did I answer the first question about the modulus?
Mm-hmm.
Okay.
Yep. We're done with that one. Okay. Number 2. Is it possible to change the material properties of a material?
When I read this question, I thought, obviously you're not it has like a connotation almost like God, like can you change the material properties of the, but I know that's not what you meant. So
Actually,
like,
that is where I was going with it.
oh
yeah.
really? Okay.
Yeah.
Can you change the material properties? The other option is to change the temperature, right?
Right.
Because if you heat up the plastic, it becomes a lot more malleable, right?
Yep.
Which I think it would decrease the slope of modulus. Right?
That's right. Yeah. Yep. Yeah. So that's a really good point. By changing the temperature of a part, you can change its properties. Where I was kind of going with this question was, for someone just starting out that doesn't have a background yet, they might think that I want to order aluminum that has a yield strength of X, but I also want to order aluminum with a yield strength of Y, because I want to use these two aluminums that are the same grade, but I just want to change the yield strength of one of them because of the application, but increase the yield strength of the other one. That was kind of where I was going, is that material properties are inherent to the material and cannot be manipulated or engineered unless you're, for example, like you said, heating it up. But as far as like properties that you can easily look up online, it might exist somewhere, but I've never really seen a chart of material properties, at this temperature and at that temperature and at that temperature. Usually you're just looking at a specific temperature, and whatever the material properties are, they are, and they're not going to change. So that's where I was kind of going with that question.
Okay.
Number 3 is kind of the same. It's really just, another nail in the coffin, so to speak. But who decides what properties should be assigned to what material? No one, really. The properties are what they are, and all we as humans do is measure those properties. But they're inherent to the material. No, there isn't like a committee somewhere that decides, okay, aluminum, we're going to give these properties, and plastic, we're going to give those properties.
Okay.
All right, so number 4, take us through a problem in which you had to decide which material to use for a specific application and how you went about deciding to use that material. Show all calculations. Okay, so let's go into our, let's see.
What about if we continue with the problem that we have at hand here with the cover?
Which one was that?
This right here, the cover for the Nintendo.
For the bending. Okay. So that would be calculating a bending stretch, which is just a little bit more complex than the one I have in mind. In this problem, we're not going to focus so much on the equation, on the calculations, as we are on how to set it up and how to look for the right material properties and use those properties in the problem. So let's say that we have a ceiling up here. This is a ceiling, and we are hanging, I don't know, let's say it's some big heavy industrial light. So this is a light right here. All right, we've got light rays coming out, and then down on the bottom is where people are standing and doing their thing. And then let's say that we've got an aluminum rod that holds this light in place. So the light is hanging from this red aluminum rod. Just color that in a little bit. And we want to know how thick does this aluminum rod need to be to support the weight of this light. So let's say that this light, let's say it equals, it's a big industrial light. Let's say it is, I don't know, 200 pounds. That's a really big light, but let's just say it's 200 pounds. So far, so good?
We also need to take into the calculation the weight of the red rod when we're calculating.
That's a good point. Yeah, the weight of the aluminum itself will have some impact on this, but for simplicity's sake, let's just say that weight is negligible, and we're only going to consider the weight of the light here.
But how one would go about calculating the weight of the rod when we don't even know the dimensions of the rod yet?
Mm-hmm.
So that they'll have to do the equation again at the end, right? Like plugging it in.
Yeah, there would be some like iteration at the end. Yeah. Okay. If you end up with a really thick, heavy aluminum rod, then yeah, you'd have to go through some iteration and add that back into the equation. But I'm pretty sure that this rod isn't going to end up being too thick anyway. So we can assume that the weight of the rod is negligible for this equation.
Sounds good.
All right, so how do we determine what strong enough is in terms of the light not causing the rod to fail because of the weight of the light? What's the engineering term? And actually, you said this already earlier, but what is that engineering term that tells us whether the rod is strong enough or not?
The yield strength point.
The yield strength, that's right. The yield strength. So if the stress created in this aluminum rod by the weight of the light exceeds the yield strength, not gonna work, right? What happens then?
Someone's gonna get crushed.
It'll start to deform what?
It's going to
Elastically
deform.
Plastically deform. That's right. It'll plastically deform. And just because it starts plastically deforming doesn't necessarily mean it's going to fail, but it is well on its way to failing if it starts plastically deforming. And there's a good chance it will fail.
Because if I understand correctly, once a material starts undergoing plastic deformation, then less stress is required to continue the deformation.
That's true. Yep, that's true. So I guess if you have a constant load on it, like we would with this light, it would end up failing if it reaches that plastic deformation.
Could be months though.
Yeah, depending on how close it is. Actually, it probably wouldn't be months. It would either fail pretty quickly or it wouldn't. Unless we're taking into, this is going outside the scope of our problem, but, if there are little vibrations that change things a little bit, then it could be months, maybe. But if it's just a static thing hanging there, it's probably either going to fail pretty quickly or not at all.
Okay. So, yeah, that's the point. Strength, yield point. Okay. We don't want to exceed that.
Right. Okay, so what one thing we need to understand is what is the stress in this in the aluminum rod? Maybe draw an arrow out there. What is the stress in there? And if we know what the stress in that rod is, then we can determine whether or not it will fail, whether or not it will reach that plastic deformation point or the yield stress.
It'll just be the force of gravity taking into account the 200 pounds of force. And from what I understand here, we don't need to do a calculation multiplying the weight, rather the mass times the gravity. 200 pounds of force is already the force.
That's correct.
In the negative direction going down.
That's correct.
So we need a material, an aluminum material, because there are many kinds of aluminum, I imagine.
Mm-hmm, there are.
A material made of aluminum material that has a yield stress point higher than 200 pounds.
Close. That has a yield strength that's higher than the stress created in the rod. And we need to calculate the stress in the rod.
Okay, let's do that.
Okay. All right. So in the equations lesson, one of the equations was a simple equation to calculate stress. Do you remember what it was? It was a very, very, very simple one, just a few variables. It was stress equals force over area. So I'm going to write that out here. So stress equals force over area. And the area that we're referring to is the cross-sectional area of the member being loaded. So in this case, what element is being loaded?
What element is being loaded? The aluminum is being loaded.
That's right.
200 pounds of force.
That's right. Yep. And let's assume that this aluminum has a circular cross section. So if I were to draw a little arrow like that, indicating that we're going to look up into that aluminum rod now, and I'm going to say our aluminum rod it looks like this. It's a solid circular aluminum rod. That's all it looks like.
So it's not hollow.
Correct.
Okay.
Yeah.
Right.
I mean, realistically, it's probably hollow, right? Because there's a conduit that goes through it for the electricity, but we're just going to make it easy and say it's a solid aluminum rod. So how do we calculate the stress in this rod? We have the equation, right? Stress equals force over area. Do we know what the force is?
200 pounds.
Right. And do we know what the area is?
The area of what?
Of the circle, the cross-sectional area of our rod.
That's what we're trying to find out.
Yeah, that's something we need to calculate, right? So once we have that answer, the stress here, let's say that we have, I don't know, 1,000 psi, 1,000 pounds per square inch of stress in that rod. What do we need?
You asked me, like, how'd you come up with that number? Because I'm seeing 200 pounds of force now. How do we come up with 1,000 all of a sudden?
That 1,000 doesn't mean anything. I was just throwing something out there to use for now. Call it X. Let's say we have X amount of stress.
Do you think that you can notate this as you're doing it?
If
needed.
Not yet.
Okay.
But let's say that we know what our stress is. We've calculated our stress in the rod. What's the next step to determining? We've already said it, but let's just restate it. Once we've calculated the stress in a rod, what's the next step in determining whether or not that rod will fail?
I'm not even sure how to calculate the stress in the rod.
Well, I mean it's this equation, right? Force over area.
So force is 200 pounds.
Mm-hmm.
And what's the area?
Well, the area of a circle. Do you remember the equation for area of a circle?
2 pi r squared.
Pi r squared.
Pi r squared.
Uh-huh.
But how do we know what the circle is?
What the radius is?
Yeah.
Well, we'll have to put something in there. We can make it whatever we want for this sample equation. But before we get too wound up with that, let's just think through the high level process here. Once we've calculated, let's say we know what the radius is, we calculated the area, now we know what our stress is. What do we compare that stress to know whether or not this rod is going to fail?
We compare that stress to the yield strength point.
That's exactly right. That's right. Yep, the yield strength. So compare that to the yield strength.
Yield strength and yield strength point are synonymous?
Yeah, I usually just say yield strength. Yield stress, people say that too. Yield strength, yield stress. Okay, so let's take a look at what the yield strength is of aluminum. And as you correctly pointed out, there are probably a lot of different types of aluminum. So here's a great website called makeitfrom.com. And it's a material properties database. I mean, you can find so many different material properties in here. It's really very useful. There's a paid version of it as well, I think, that gives you, even more. I've always just used the free version, and it's been sufficient. So here we got aluminum alloys. Let's see what we've got in there. We can really look anywhere in here because right now we're just kind of exploring to see what aluminum yield strengths are. 6,000 series aluminum is a very common series. So why don't we take a look in here? And I happen to know, just because of past experience, that 6061 is, in fact, 6061 is a very common grade. 6061 T6 is one of the most common grades of aluminum. So we've got T62. I don't really know what T62 stands for, but here's 6061 T6 right here.
This can be a little overwhelming for a beginner that looks at this website for the first time.
Okay.
Too many options. So where does one even start? What's the first aluminum that I should be clicking on?
Well, it kind of requires that you have an understanding of some really common materials. So one of, let's see, I believe in the material properties, yeah, there's a list that we provided, and these are some really common materials. So 6061 T6 aluminum is something that's listed there. And I don't know of an easy way for a person to like evaluate all of these. These are just things that I have learned and remembered over time. But if someone had given me a list like this at the beginning and said these are some really common materials that are used very frequently, it would have been super helpful. I would have known.
Guys. You're welcome.
I would have known exactly where to go to start looking at what material properties.
What about if we go back to the website, please? 6061 does the number that was in the 6061 as it increases, does it increase? No, they're all 6061 dash T51, T4. So the number after is 661. I'm looking over here. Let's say the T1, T42. Does that number have a correlation with the yield strength point?
It does, yeah. That T number represents temper, so it's tempered in different ways in order to produce different properties.
So does the higher number after the letter T indicate a higher yield strength point or lower?
I'm not sure. If you're using aluminum, probably 95% of the time you're going to be using 6061 T6 aluminum. So just remember that particular grade. It's almost always used as a mechanical designer if you're using aluminum. I mean, it's so common that when we create drawings for our engineering projects, we have a drawing template, and one of the options that we have in a little drop-down menu is 6061 T6 aluminum because it's just so common.
Okay. Sounds good.
Okay, so if we click on that, we've got a bunch of properties here. And, Raph, you made a good point that this can all get kind of overwhelming for people in the beginning. So don't feel like you need to, remember all of these different properties or even understand all of them because there are a lot here. But all we're looking for right now is the yield strength. So we've got, I'm just going to kind of read through these. Hardness, Young's modulus, elongation, fatigue, Poisson's ratio, shear modulus, shear strength, tensile strength, ultimate, and tensile strength yield. So that last one, tensile strength yield, this is the one that we're after. That is our yield strength. And it tells us that it's 39 times 10 to the third psi. Now 10 to the third is just scientific notation. All that means is 39 with 3 zeros at the end of it. So our yield strength is 39,000 psi.
Per psi, what does that mean?
Pounds per square inch.
Okay.
Yep. And then over here on the left side it says 207 MPa. Now PA is pascals, which is the metric unit of stress or pressure. So it's giving us the same thing, just on the left side is metric and on the right side is English units. M, if you're wondering, M stands for mega pascal. So mega means add another 6 zeros. So it's 270 plus 6 zeros pascals, or 39 plus 3 zeros psi. So far, so good?
Yeah.
Okay. All right, so let's go back to our notes here. We'll say yield strength equals 39. I'm going to write KSI because this is a common way of writing. KSI is 1,000 PSI. KSI equals 1,000 PSI. So 39,000
What's a KSI?
PSI equals 39 KSI. And KSI just stands for kilo. And then you kind of lose the pounds in there, but it means kilopounds per square inch is what KSI stands for, right? A kilo, what is 1 kilo?
1,000.
Right, 1,000. So KSI means 1,000 PSI. And that's a common way of writing it that you'll see a lot.
Okay.
All right, so we know what our yield strength is now. Now we need to solve for our stress in that aluminum rod. So let's see. some of this is kind of up to us. Let's impose some restrictions on ourselves and just see what happens. Why don't we say, or maybe, let's see, shall we solve for the point at which our aluminum rod will fail, and then we'll know that will be based on the diameter of the rod, and then we'll just know that the diameter needs to be at least that big.
Is that how you
for
would
it not
usually
to
do it in
fail.
real life?
Well, it depends what they're asking you. I mean, if someone were to give you a radius and just say, will this fail, then you could solve it directly. But as of yet, we haven't given ourselves a radius. We could do that way too, though.
Let's do it the easiest way first.
Okay.
So they give us the radius.
All right, so let's say our radius is what? How about half an inch?
Half an inch?
Mm-hmm.
Okay, it's just like this.
Half an inch is like, maybe like that.
Okay.
Half an inch. Pretty small.
Pretty thin.
Yeah. Okay, well, let's see what happens. Sounds pretty thin, so it sounds like Raph is worried that this thing's going to fail.
I'll be concerned if I've been walking under that.
All right. This is the wonderful thing about engineering equations, though, because the numbers will tell you whether or not you should be concerned. And sometimes you'll be surprised at the results. So this is why I love engineering. Okay, so we know what our radius is. We have our equation, stress equals force over area, right? So area equals pi r squared, or I like to do pi, well, I guess we're starting with radius, so we'll just leave it like that. So equals 3.14 times 0.5 squared. And Raph has got a calculator. What does that equal?
Alright, so 0.5 squared. Like this?
Mm-hmm. Okay, 0.785 equals 0.785. All right. So then how do we plug this into our stress equation, Raph?
We would do the force, which is 200 pounds of force, divided by this area.
Okay, 200 pounds of force divided by 0.785. Do you want to calculate that value for us?
Alright. 254.77.
254 point, I'll just put 0.8. And what are our units?
It would be pounds of force over, and this one's inches squared. Yeah.
Right. What's another way of saying that?
Is that PSI?
That's PSI, pounds per square inch. Right? We've got pounds on the top, inches squared on the bottom. Pounds per square inch.
Wow. Okay. PSI.
PSI.
Don't tell me what's next. Hold on. Let's
Okay.
see if I can figure it out.
All right.
So, our stress is 254 PSI.
Mm-hmm.
Just round it up. 255. So, the PSI that we have is 39. So, this will definitely break.
Look at the units.
KPSI. So, what about regular PSI? What's a regular PSI? That's it? Okay, so this is. So we're comparing these two.
Mm-hmm.
Yeah, this one's much larger.
It is.
So we'll be fine.
We'll be fine. Yep. Yep. Now.
We'll be more than fine.
Oh yeah, there's like no chance that this is going to fall at a half an inch. Right, so we were thinking half an inch, that sounds kind of small. Are we going to be okay? But what we're seeing here is that we're more than okay. So this is a good segue, actually, to talking about factor of safety. Now, factor of safety is essentially just how do I say this? How far above and beyond your calculated stress you can be before you actually fail. So we're saying we're about
Think about that. Hold on. How far beyond? Say that again, please, slowly.
It's not a good way to say it. I don't think I defined it very well. I think that let's keep talking here, and it'll become more evident. So we have about 255 psi of stress in our aluminum rod, and we know that we can have up to 39,000 psi before we reach the yield strength of the aluminum rod. So we've got like plenty of room in there. Now, I just said we have plenty of room in there. Let's define how much, like how many times, 255 times what until we get up to 39,000 psi. Like how many times can we multiply 255 until we're at 39,000 psi? Raph is doing some math here.
52 times.
So 39,000 divided by 255 equals 152.9. I'm just going to say 153. So 153 is what we call our factor of safety. So we have a factor of safety of 153 here.
I remember this from class, another class I'm taking, that products, depending on their industry, have different factors of safety, right? And the automotive industry has a certain amount of factor, etc. And even hardware has different factors of safety, right? The more factors of safety, the more expensive the hardware is, right? Like a screw that has like a very high factor of safety,
Yeah,
like
okay,
8.
sure.
Okay.
Yeah.
Sorry, yeah, keep going.
Okay.
I just want to make sure I connected those dots.
Yeah, absolutely. So 153, that is a huge factor of safety. And typically, if you're designing something and you see that you have 153 factor of safety, you know that you have over-designed something. And usually that means you're designing something that's going to be more expensive than it needs to produce.
Exactly.
So you usually, I mean, I'm going to give you kind of a rough rule of thumb here, but a lot of things that we'll design, we have, between 2 to 4 factor of safety, 2x to 4x. And so we've got 153 here. We've got way more than we need to. So let's kind of back into this now and go back towards the beginning of the problem. And instead of saying we have a half-inch radius, let's instead say, what radius do we need in order not to fail?
So I guess we use the same equation to do it like this. Alright. So the equation will be the same, but we know, let's see, stress equals force divided by area. We want to find an area. Really, we want to know the R. This is the one we're going to change. We know the force will continue to be 200 pounds of force pi r squared. What is this R? How do I calculate it? Any hints?
Well, let's think about what are you trying to solve for. Let's go back to the original question. What is the question we're trying to answer now?
How much the radius should be. Because if we adjust the radius, we want to end up with a number that ends up being 2, 3, or 4.
Yeah, and for right now, to start with, let's find a radius that makes the factor of safety 1. In other words, there is no factor of safety. We're just solving for the exact radius that will produce an aluminum rod that's it's at the failure point of yield stress. And once we know that, then we know, okay, so our radius just needs to be bigger than this in order to not fail.
How would I go about finding that? I'm thinking.
Write out your equation again, your stress equation, and this time don't plug any numbers into it, just use the variables. Okay, now break A down. What is A equal to? What's the equation for A? Okay, now write the whole equation out again using pi r squared in place of A.
Did I plug in the 200?
Nope, not yet. Okay, and then equals, and we're going to use the Greek letter sigma for stress. Do you know sigma? There you go. Yeah, that's the, I think actually I said the wrong, I said rho in an earlier video and I made a mistake. Anyway, sigma is that is sigma, and that's the Greek letter that represents stress. So we've got sigma, we've got force, and we've got radius. Those are the three variables we have in this equation, right?
Too many variables for one equation, yeah.
Well, okay, what are we trying to solve for?
R.
Okay, all right. So next step, let's solve for R. This is just some algebra.
Okay. So I will multiply by pi r squared by pi r squared. So F equals sigma times pi r squared. And now we want to get rid of, let's see. So these two we multiply, we divide it by sigma.
Mm-hmm.
Sigma equals pi r squared.
Yep.
And we would divide this by pi.
Yep.
So equals r squared, and then we'll square root it.
Now hold on, let's stop here for a second. When you divide it by pi on the right side, cancels it out. But on the left side, where does that pi end up going?
Or I guess you could multiply it by 1 over pi.
Mm-hmm, right? So instead of writing f over rho over pi, how do you write that just with a single numerator and a single denominator? There you go, yep. Or just f over rho times pi. Ugh, I keep saying rho, sigma times pi.
Equals r squared, and then we square root.
Uh-huh. Okay, cool. So now you solved for r. So now let's think about this equation. What does this actually mean? What does that, if we were able to solve for r, what is that telling us?
That when we have this radius on the rod, we have the exact, this is the exact amount of radius needed for us to be at the yield strength point.
Exactly.
So if a fly lands, if a fly just happens to land here, this thing will start.
That's right. Look out below.
Well, not necessarily, like you said before. It will just start the process of plastic deformation.
Mm-hmm. Yeah. Right. Okay. Excellent. So, what variables do we know in here?
We know. Do I start plugging them in?
Mm-hmm.
200 pounds of force. We know sigma stress. Do we know sigma? I'm thinking that's the stress. But in order to calculate the stress, we would need to know the radius. So how could we possibly have sigma then?
All right, good question. So go back to like what this equation actually means, right? You just said this is the equation that tells us the radius at which we're going to be at that exact yield stress point of the material. So if this equation is meant for us to solve for R at the yield stress of the material.
So we plug in the yield stress.
That's right.
Sigma.
Yep.
But I thought sigma was stress.
It is. It is.
So 39,000 psi.
Because 39,000 psi is the yield strength, right? That is the point at which yielding will begin to occur.
Times pi.
Okay, we're going to do some math here.
200 divided by 39,000, well, actually parentheses. Gee, I haven't done this in a while. 200 divided by 39,000 times pi. Got that answer. Then I try to square root it, and it gives me an error.
Yeah, I don't know. Well, what's the square root of, what was it, 0.0016? 200 divided by 39,000 times pi is 0.0016. So what's the square root of 0.0016? Point 0.04. Okay, so that's our radius, 0.04. Now, I think that diameters are a little bit easier to think about just conceptually. So if our radius is that, what diameter is our rod going to be?
Just times 2.
Right, just times 2. So that's like 0.80, right? 80 thousandths of an inch.
Yeah.
So that, what's that telling us? 80 thousandths of an inch. What does that mean?
It's like a string almost. It's very thin.
Pretty thin, yeah.
Might as well get a wire.
And in fact, oftentimes you will use a wire rope to hang something like that. But it's surprisingly small, isn't it?
Yeah.
Yeah, 80 thousandths of an inch. That is, a credit card is maybe 30 thousandths of an inch. So this is like 2.5 credit cards thick or something like that, but a circle.
Okay. Want to do a breakdown?
Okay, Raph had a few questions about this, so I'm going to turn the time over to Raph, and he can ask these questions, and then we'll discuss.
I wanted to know what the calculation would be like if the screw is hollow. So only this area. It's solid.
Okay.
Well, you don't see a rod connected to a lamp and nothing to connect it with. You're going to need screws. And to have screws, it's probably going to look like the rod. We have something around it that goes like this. This is going to be very thin. And then we're going to have screws on it, or like bolts right there. And then the lamp. This changes our stress, because stress is force divided by area. And our area has changed now. It's not this rod. It's like thin, almost like a thin sheet. And I was wondering how that would change. So hollow, and then make it this area here.
Okay. Great questions. Let's talk about the hollow one first. Let's scroll down here, give ourselves some room. So let's see. Our equation is sigma equals force over area, right? And we're saying, what if we have a cross-sectional shape that instead of being hollow, it's just like this, where this is, this is solid around the outside. It's like a donut, right? Looks like a donut. In that case, our equation doesn't change. Stress still equals force over area. But now, what is the area that we're solving for?
it's not the entire thing anymore. It's just the area with the solid.
That's exactly right. So how would we calculate that?
I haven't done calculations like this since I was like in 6th grade. I know it has to do with pi r squared. I don't know, how do you calculate the area of a hollow?
Yeah. So let's break this down a little bit. Okay. Let's say that we'll just call this inside diameter the blue circle, and then the outside one is the red circle. All right. So what we have is we've got a red circle, right? And we've got a blue circle. And what's the equation?
I got it.
You got it?
Yeah, so just do the pi r squared for this one, do the pi r squared for this one, and then subtract it.
That's exactly right. Yep. And that's your new area. Okay, so that one makes sense? The cross section?
One more. This is implying that they gave us a tube already. They told us, like, look, this is your area. But what if, is that usually how it works? Like, you have different areas of tubes to select from, or you create your own tube?
Yeah, it could be either one. I mean, if you're trying, let's say that you're only making 10 of these things, right? So you don't want to go off and open up new tooling at a production factory because that's expensive. You probably just want to pick from something that's already off the shelf. So you could go to McMaster and look at what stock off the shelf tubing do they have and use those dimensions.
And then do the calculations for those dimensions?
Yeah.
Wouldn't a website like McMaster already tell us the information such as the stress yield point?
They'll tell you what the stress is, yep, the yield stress, but you need to compare that yield stress against the stress produced within your shape, right, within your rod. So you still need to calculate the stress in the rod, and to do that you need to calculate your area or know your area.
So if we were to plug that into this one, the force will remain the same, 200 pounds. The area, we'll do the calculation and give us the area. And once we calculate this, it's going to give us the stress. And then from there, we take the stress and we do the FEA equation.
FEA is finite element analysis. That's a computer simulation.
Oh, sorry. FOS.
Ah, yes. You could do the factor of safety, yep. Yeah, which is really just comparing it against your known yield strength of the material, right?
Okay.
So let's say that we did plug it in. So we've got this equation boxed in blue, and instead of using the solid circle for area, we're going to have just a hollow tube. Now, we don't need to actually calculate any values, but assuming we put a hollow tube in there, is the area going to be more or less than the solid rod?
It's going to be less.
Right. So what happens if your force stays the same, but your area is less? Does your stress go up or down?
So we're going to be dividing this same number, because it's the same material, by this was the stress. So will this number be bigger or smaller? That's the question.
Well, what you're looking at right now is factor of safety. I'm just talking about stress. So this boxed in blue here.
But the stress is plugged here, right?
No. Well,
what was the stress?
We're not even there. I'm just saying, look at this equation boxed in blue, just looking at the stress value, not even looking at factor of safety at all. If you used the area of a hollow tube as opposed to the area of a solid rod,
higher stress.
Higher stress, yeah. Right? So smaller cross-sectional area, higher stress. And like intuitively, does that make sense?
Yeah.
Yeah.
You can have it's like the example that I saw on YouTube of magicians when they sit on a bed of nails and they put another I don't know, like a door full of nails on top of it, and then they have a person stand on top of the door nothing happens because the force is distributed to the nails.
Mm-hmm.
But
Yeah.
if you only have like one nail, all the force will go to that one nail.
Right. Yeah, exactly. Okay. Anything else you want to cover there?
This here, how would that change?
All right. So now let's talk about this. We've got this would be referred to typically as a flange. A flange would be that plate with the screws going through it. When we're looking at the equation stress equals force over area, the area that we're calculating, we always want to look at, how do I say this? Like the area that's the weakest, I guess, or the area that's most likely to result in that failure. So, like if we had, I'm just going to draw a rod. We're looking at the side of a rod. If we had a rod that looked, something like this, and we have a load. We're pulling down in this direction by whatever, we'll say 200 pounds, just like this example. And then maybe it's fixed up on the top here. Where is this rod going to fail? Is it going to fail here? Or is it going to fail here? Or is it going to fail here?
The second one, the middle.
Middle one, right? Because that's our smallest area. So our stress is going to be highest right there, which means that is the most likely point of failure. So going back to this example where we've got a flange, right? A flange with screws going in. What is the connection here between that flange and the light? Like what is actually holding that flange to the light?
So what that would look like is, I guess you call this cross section, but this is the pole, I suppose. And you got some screws here. This is right here. That how wide that is, how thick this part is.
Like the diameter of it, you mean?
The diameter would be from here to here, right? To here. But I'm thinking rather how thick it is.
Okay.
And that would be the area of, I suppose, most stress, or
Now,
more likely to break.
Why do you say you're referring to the diameter of the flange itself? Why would that be the diameter to consider?
Because it's thin. Like just regular intuition tells me like it'll probably break here. If like there will be vibrations in the building, it'll maybe break from here or no.
I don't know. Let's see, how do I say this? Let's go back to our equation, right? Stress equals force over area. So it's kind of up to us as the designer to determine what that area is. And going back up here, we determined that we want to look for like the smallest area or the area that's most likely to fail. And that's what we're going to use in our sigma equals F over A equation.
So then we'll be looking at this part.
Certainly.
That's less area than this.
So that's I would say that's a question, is this area less than the area down with the screws? You could, in fact, you probably would want to do a few different calculations. You might want to do one where sigma equals F over A, and we'll just say A of the rod, So this diameter right here. We'll say that's the diameter of the rod, and we would use that to calculate the area of the rod. But the other equation, so the other place where it might fail, and this is why I was asking, what is the actual connection of this flange to the light? Is the entire flange connected to the light? Like, if you look kind of like, I don't know, up like that, you're going to have a flange. Let me try. You're going to have the circular shape of a flange, right? And then you're going to have the light that's kind of around the flange. Is this entire surface area of the flange like fixed to the light underneath it?
Only the parts that have the bolts on it.
That's right. Only the parts that have the screws on it, right? So if we draw this again, we've got our flange, and we've got our light that kind of surrounds it. The only part of that flange that's actually holding the light is these screws, the diameters of those screws. So the second equation that we could do is...
So then we figure out, we gotta get on McMaster website, find out the radius of the screw, or the diameter of the screw.
Yep.
And then we find out how many screws we need.
Right.
Because all the stress is gonna be on the screws.
Mm-hmm. Yep. That's exactly right. Now, let's take this one step further. What material are screws usually made out of?
Steel.
Steel, right. So if that's the case, are we going to use the same yield strength that we used before?
No, but that should be on the McMaster website too, right? They should tell us the yield strength for that particular material that the screw is made of.
It probably... In fact, what McMaster will probably tell you is that, yeah, you're right, the yield strength for that screw. Yep. And if not, you estimate it. McMaster will tell you what the material is, and you can go off and search for yield strength for that particular material.
See, the thing is, I don't want to be taken all day with this equation. I just want to know, okay, how many screws do I need exactly to meet my, yield strength, just to meet it, a 1-to-1 ratio.
It's a good way to do it.
And then be like, okay, I'm just going to put like a couple screws more.
Yep.
So how would you go about doing that calculation? I'll just watch you. How do you do that?
Okay. So what I would do is, let's see.
This is the proper way of doing it, right? You go this approach?
Mm-hmm. This is what I would do. Okay. Yeah, absolutely. So let's see. I would derive my own equation and then solve for whatever variable I've determined is the one that I want to change. So we'll have to make a few assumptions here. Let's talk about the variables. We have, well, let's start with our equation. F, or sigma, equals force over area, and area is pi r squared. And the pi r squared, we're going to break down even further because there are multiple fasteners and each one has its own area. So I would say equals F over X, pi r squared, where X equals number of bolts or number of fasteners, number of screws, whatever. Let's just assume steel. We're going to assume a steel material so we know what the yield strength is.
Steel material for the screws.
For the screws,
okay.
That's right, yeah. And we know what our force is, so we'll say, known variables. We know what our yield strength is. We know what our force is. Unknowns right now are, so let's see, unknown would be the number of bolts, and I guess for starters we can say the radius, but we're going to have to start with something. So what we could either assume a fixed number of bolts, or we could assume some radius. And I would probably start with assuming a known radius, because different screws, there are standard sizes of screws, so you're only going to have so many options. So maybe you want to use, quarter 20 screws, in which case your diameter is 1/4 of an inch, your radius is 1/8 of an inch. So now this radius moves over to our known column, right? And now x is our only unknown. So then I would solve for x, right? So we say...
How do you know sigma though? Because to know sigma, you have to know everything else.
There are two, think of it as two different sigmas, right? One is the sigma that you're solving for, and the other one is the yield stress.
But why do we have the same variable for both of them?
It depends what you're trying to solve. If you're trying to solve for, that exact one-to-one point at which you meet your yield strength, then by definition you're solving for that material's yield strength, and it's just material based at that point. You have to use the yield strength associated with that material.
Okay, so what's the yield strength of steel?
I don't know what it is offhand. It's probably 50 KSI or something like that. It doesn't even matter, though, for what we're doing right now. We're just solving. So x is the variable that we want to solve for, and then it's just, some algebra to solve for that. It would be x equals force over sigma pi r squared. And that would tell you, assuming a 1/8 of an inch radius for a 1/4 inch diameter bolt, this would then tell you how many of those 1/4 20 bolts you need to be at the yield strength. Does that make sense?
Yeah.
And since we found earlier that we only needed a 80,000th diameter aluminum rod to hold 200 pounds, I mean, we kind of know that just a single 1/4 inch bolt is going to be more than enough to hold our 200 pounds. So, make sense?
Yeah. But now I'm thinking, we could just end a very nice point. But I'm thinking the dimensions of a screw. Okay. The dimensions of a screw. Let's say this is the flange, I suppose, and the light is here. The stress of the screw, where is the most stress of the screw? Because when we say the diameter, we're looking at the diameter here.
Mm-hmm.
And that is correct, because looking at the diameter of the place that has the least area. And least area means that there's going to be more stress. So we're doing the calculation for the area that has the most stress. Would probably be here, right?
Right.
Because this is going down. Okay.
Yep. Exactly.
Yeah, it's nice to know how things work. The math.
Yeah, it's cool, isn't it?
I like engineering. It's
I
cool.
do too.
If you found this content helpful, consider enrolling in our signature program at mypipelineacademy.com. Whether you're an individual interested in beginning a new career as a mechanical designer or a company interested in training your new engineering hires, our signature program helps students develop the practical skills they need to be productive mechanical design engineers. Seating is limited. We hope to see you there soon.